So our last section in this area of stereochemistry gets us into an area known as chirality. And when we talk about chirality, we're now dealing with molecules where the formulas are the same and the connectivity is the same. So what I'd like you to do is to put two models together. And I'd like you to put them together exactly the way that they're being drawn here. And so you can see we've got a carbon in the middle in both of these that's connected to the same four groups: hydrogen, bromine, chlorine, and methyl. And so I'd like you to take a minute and see if you can superimpose these molecules onto each other. In other words, are these the same molecule? And so what you find, or should find if you put these together correctly, is the formulas are the same, the connectivity is the same, but their three-dimensional arrangement is different. And you're not able to superimpose them. So they're not actually the same molecule. So this is an aspect of what we define as chirality. A chiral object is one that has a certain characteristic to it. So again, if you look at the two molecules that you put together, what you should see is that in one case, we know they're not the same. But a second aspect they have is that they're actually mirror images of each other. Can you think of any common everyday objects that you might have that are mirror images, but you can't superimpose them? And what this should make us think of are, for example, our hands. If you put your hands next to each other, your hands are mirror images of each other, but you can't superimpose them. So a chiral object is one that possesses what we call handedness. And these are important in chemistry. They're also highly important biologically. In fact, almost any type of biological molecule that you think about, whether it's DNA, sugars, proteins, amino acids, and the list goes on, they're all chiral molecules. And depending on which version, which form of them you have, can make a big difference in how they behave and how they function. So overall, we call this class of molecules stereoisomers. So again, these are molecules, same formula, same connectivity, different 3D arrangement. All right, so now how do we define or find one of these chiral objects, chiral molecules? So a chiral carbon is one that has 4 different substituents. And when we say different, that could be something very obvious, like this carbon. But it's also just literally any point of difference in the molecule. So up at the top, we've got 7 carbons on that group. At the bottom, we've got 8 carbons. Even though that difference in these two chains is 7 carbons away, it still means they're different. And so this would also be considered a chiral carbon. Again, the groups, any difference in the groups makes them different. So what we find is that the presence of one chiral center in a molecule this guarantees that the molecule itself is chiral. But interestingly, a lack of chiral centers does not guarantee an achiral molecule. So achiral, meaning not chiral. Most molecules that have no chiral centers are not chiral. But as we'll see later on, there are some exceptions. So in other words, it is possible to have a chiral molecule that doesn't actually have any chiral centers. And also, 2 or more chiral centers is usually chiral. But again, we will see some exceptions. There can be molecules that have 2 or more chiral centers and are not chiral. Now, finally, any carbon with 2 identical substituents is achiral. Now, it's important to note that chirality is not the same thing as we talked about, just before this with the idea of conformational isomers. If you want to interconvert between 2 of these stereoisomers, you actually have to break a bond. It's not just a bond rotation. Now, there's some history that can be interesting to get into as it relates to chirality. And the idea of chirality goes back, quite a ways. And it's credited to Pasteur, who we're probably familiar with from, among other things, pasteurization. Now, how did he observe stereochemistry way back, in 1848? Well, he was looking at the following compound. This is known as plus tartaric acid. And it's actually found as a byproduct from making wine. And what Pasteur did was he was comparing this tartaric acid that was isolated from making wine, and he compared it to another sample of tartaric acid that he had gotten from a lab somewhere. And he found that there were two different types of crystals. In fact, amazingly, he was actually able to separate the two different types of crystals with a magnifying glass and tweezers. And trust me when I say this is not common at all. But he was able to do this. And he observed that the crystals themselves were not superimposable. And so among other things that he did, he took each of these samples and dissolved them in water and placed them into a polarimeter. So a polarimeter is an instrument that it will rotate light or measure the rotation of light. Light consists of two perpendicular fields and vibrates in all possible planes. But when we pass it through a polarimeter, the light only oscillates in one plane. And so we then call it plane polarized light because it's only operating in one plane. If we have a chiral molecule, and only if we have a chiral molecule, the chiral molecule will actually rotate the plane of the light. And then that allows us to calculate something known as a specific rotation. Specific rotation is equal to the observed rotation, so whatever we get from the polarimeter, divided by the concentration of the sample and the length of the cell, but given in decimeters. But this then becomes something that you can measure for any chiral molecule. And this was what Pasteur did. And what he found was very interesting. He found that the two samples of tartaric acid each gave the same amount of rotation, but in opposite directions. And so while this was obviously very new in 1848, we now know if we have two molecules that are mirror images of each other, they will rotate light the same magnitude, but in opposite directions. And so if you're wondering what this plus means, well, this was the way that these types of chiral molecules used to be named. So if the rotation of the light was clockwise, that was referred to as dextrorotatory, or D, or plus. If it rotated the light counterclockwise, that was referred to as levorotatory, and L, or minus. All right, so that was, the end of the story for a little while. But about 25 years later, two other chemists would show up, and Lebel and Van Hoff each made a proposal. Now, interestingly, they made this proposal independently. If you think back to the way things would have been in the 1800s, communication obviously didn't happen anywhere near as quickly as it does now. So there are cases like this. There are other cases where, two scientists discovered the exact same thing, working completely independently. So what did Lebel and Van Hoff propose? Well, based on what Pasteur found, as well as other results, they became the first to propose something very radical. Although it might not seem that way. They proposed a tetrahedral structure for carbon. And Van Hoff especially would, go on to quite a few other accomplishments. In fact, Van Hoff won the first ever Nobel Prize in chemistry in 1901. But this idea of carbon being tetrahedral was not necessarily all that well accepted at the time. Hermann Kolbe, who is regarded as one of the founders of organic synthesis and is known for, among other things, the Kolbe-Schmidt reaction, published the following statement in response to this proposal of carbon being tetrahedral. Not long ago, I expressed the view that the lack of general education and of thorough training in chemistry was one of the causes of the deterioration of chemical research in Germany. Will anyone to whom my worries seem exaggerated please read, if he can, a recent memoir by Herr Van Hoff on the arrangements of atoms in space, a document crammed to the hilt with the outpourings of a childish fantasy. This Dr. Van Hoff, employed by the Veterinary College at Utrecht, has, so it seems, no taste for accurate chemical research. He finds it more convenient to mount his Pegasus and to announce how, on his bold flight to Mount Parnassus, how he saw the atoms arranged in space. So Kolbe, while a very, very important person to the history of organic chemistry, would appear that he got this one wrong.